All right, so pre-stacks are arbitrary functors. Think of them as Grothendieck functors of points of something. You have a gadget and you say what it takes to map an affine scheme to it. So in this world, if you have two such gadgets, y1 and y2, there is what I call the mapping stack, mapping space. And it's another gadget of the same form. It's an internal home that you guys must be very comfortable with, and it's defined as follows. It's exactly what Laurent said. You say that home from the test affine scheme to this is by definition home from S times y1 to y2 in the category of pre-stacks. Okay. So, and as an example, so I wrote bun G. Sometimes I forget even to give the definition, because how can someone not know this notation? Indeed. But what it is, it's really the mapping stack from the curve to BG. And so this I think I wrote, log sys is the mapping stack from X deram BG check, and X deram I introduced last time. Let me just write it again, so like just for fun. So like home from a test affine scheme S to something deram is by definition home from the underlying reduced classical scheme to Y. All right, so just to recap who the geometric players were. So another player was the category of quasi-coherent sheaves, and so you can write it as a limit. When I see the symbol limit, I get scared. So just concretely, what it means is that an object of the category of quasi-coherent sheaves on a pre-stack Y is by definition your knowledge of its pullbacks to all affine schemes. It's for every S mapping to Y, you specify F sub S little y inside quasi-coherent sheaves on S compatibly with pullbacks. All right. And now I've been speaking too much, I want to ask the audience a question. So let G be a group pre-stack. So it's a group object in the category of pre-stacks. And let V be a vector space. I want someone to improvise the definition of G acting on V.
What is V?
Vector space. Again, in the spirit of Grothendieck. Impersonate Grothendieck and give me the definition. Let's forget about this Fourier-Mukai transform. This is more important and basic. Let's just have fun. So, somebody, give me the definition. Go for it. Grothendieck would not like it.
Maybe a map from G to the endomorphism?
He wouldn't like it either. He liked families. That's a hint.
But your group pre-stack is living on something.
It's over point. It's like
Just
over point, yeah. And that's why this is like a vector space. It's like a sheaf on the point, yeah. You can think of a base, like V is a quasi-coherent sheaf on the base, and G is over a base, but base is the point. Yes?
So for each object on the base category that the stack is defined in, we correspond certain vector space for associated to each V. Then we consider the automorphisms and the
Yeah, so Grothendieck likes it more. So like here's the actual definition. So for every affine scheme S, you do the following. So you consider your V and you tensor with OS. You consider it as a quasi-coherent sheaf on S. And now you consider HOM from S to G. And that's just a group. And what you do, you make this group act on this guy in the naive sense, like really group acting on an object, forget all linear structure, in a way compatible with pullbacks. So that's so now theorem. So quasi-coherent sheaves on BG. So what's BG? Well, do you guys know what BG is? What I mean, like classifying space of a group? Yeah, so it's
Most people know, but not everybody.
yeah, so if you have a group, you can create, okay, let's do it, Grothendieck spirit. So I have to say HOM from S to BG is, well, it's B of HOM from S to G. So this is a group. Now I have to say what this is. So if you have a group, you can create a groupoid which has one object, and morphisms are given by G, and compositions are given by multiplication in G. So that's the meaning of B. And you also give yourself a Grothendieck topology. So you do this, and then you sheafify. It's kind of not very important for us to sheafify because quasi-coherent sheaves satisfy descent for all the topologies that we consider, so sheafification won't do anything. We just can state like this. So that's BG. So theorem, this is the same as rep G, by which I mean vector spaces with an action of G in that sense. So theorem. Normally, I would have asked a member of audience to prove it. Let me not do it now because it would take 10 minutes to unwind. It's a really good exercise. Like, go home and do it. It's an exercise on what prestacks and quasi-coherent sheaves and prestacks are. You really unwind. Where was I? Okay. So here is a recap of some other things we did. Let's say gamma is a finite abelian group. So you have this pairing gamma check to GM. Gamma check is the Cartier dual. It really classifies maps from gamma to GM. And so you can B it. So from here, you obtain a pairing from B gamma times B check to BGM. And a map to BGM from something is the same as line bundle on that something. And that kind of operation defines you by a formula, this one Fourier Mukai transform. And in this case, this one Fourier Mukai transform will be an equivalence. So it's like Fourier Mukai will be an equivalence between quasi-coherent sheaves on B gamma and quasi-coherent sheaves on gamma check. But again, gamma check was a finite abelian group, so it's really kind of the most stupid algebra geometric object, discretely many points. So quasi-coherent sheaves on that is just vector spaces indexed by points of gamma, or graded by points of gamma. And this, we just said what it was. This is representations of the group gamma. And what this Fourier Mukai says, it says something very familiar. Like, go back to your undergrad, representations of finite abelian groups. It says that a representation of a finite abelian group you can decompose it according to characters, and that's what this does. Like to specify for each character, you have the multiplicity space. This is what this equivalence does. All right. Question to the audience. What else did we do yesterday? What other words were pronounced? You don't have to say what these words mean, but just say what the words were. Oops. All right, I'll give you a hint. We talked about sheaves of categories. So again, you have a pre-stack Y. I want to define, and it's in the spirit of the definition of quasi-coherent sheaves. Only this will be a two category. So I have to tell you what objects of this two category are. And they're defined really like quasi-coherent sheaves. And that's where these tensor products of categories come up. So an object, let me call it C underlined here, is the following thing. It's for every affine test scheme S and a map to Y, I call this it's an S, we call it an S point of Y, denoted little y. To it, we attach now a category, call it C sub Sy. So in the case of quasi-coherent sheaves, we had a quasi-coherent sheaf on S, which is the same as a module for the algebra of functions. S was an affine scheme. Here, you're kind of one categorical level up. It must be a module, but for the category of quasi-coherent sheaves on S. So again, you're one categorical level up, and you start doing algebra in DGCat. So you have an algebra object in DGCat, this category of quasi-coherent sheaves, and you act by it. Plus compatibilities in the same way. And so theorem, you want to classify sheaves of categories on BG. Very similar to this. And what we say, this is, you can call it 1 rep G. So these are, before, these were representations of G, i.e. vector spaces with an action of G as defined here. Now it'll be same thing, categories with an action of G. And if you want to know what it is, you just improvise from that definition. Just one categorical level up. All you have to know is that every time here the symbol was tensor with OS, now you tensor with quasi-co-S. So it's like categories with an action of G. All right. Okay, let me recap a few more things and then we'll go to the topic of today's lecture. So, see, here's one operation. You can do with sheaves of categories, which is better behaved than the analogous operation with quasi-coherent sheaves. Suppose you have a map F1, Y1 goes to F2. So the point is that in this case, there is a direct image functor from sheaves of categories and in fact, so there's a pair. Again, this is very topos theoretic. So this guy is defined tautologically because you see, like if I have a sheaf of categories, of y2, I have the ability to evaluate it on every s point of y2. And I want to create a sheaf of categories on y1. So I want to evaluate it on every point of y1. And what I do, I just compose. So if I take the pullback of the sheaf of categories and I want to evaluate it on s comma y1, where I, by definition, evaluate my original sheaf of categories on the composition. And this operation has a right adjoint. It's called the direct image. So and here is what it is concretely. So what I mentioned is that if you have an arbitrary pre-stack and you have a sheaf of categories, so let's say this is a sheaf of categories on Y, you can take its global sections. And this is by definition, like we defined quasi-coherent sheaves. It's the limit over all affine schemes mapping to your Y of these categories. And like when you define direct image, it's very much like you do it with usual quasi-coherent sheaves. So here's your y1 to y2. You start with a sheaf of categories on y1, and you want to create one on y2. So, and what you do is the following. You form the fiber product. And let me call it y2 prime. And you say that the value, this is f, of f lower star of C underlined on S comma y2 is global sections on this fiber product of the pullback of the sheaf of categories to the fiber product. And if you unwind, this will be the formula that you get for the direct image functor. And the point is that this operation is always well defined. It's much better behaved than the direct image for quasi-coherent sheaves because it exists under no assumptions. All right. What else do I need to recap? Nothing. All right. And the last thing, no, I need to recap one more thing, gerbs. So if A is an abelian group stack, you create B to A, which is B of A. And definition, an A gerb on Y is the same thing as a map from Y to this B to A, sheafified in your favorite topology. So these are gerbs. And what we need two operations. So one operation is this, that if A is GM, and if you have a sheaf of categories C, and so suppose you have so this G is a GM gerb on Y, and so C underlined with a sheaf of categories on Y, you can twist it. You can create, and it's a new sheaf of categories. And this is completely analogous to if you have a quasi-coherent sheaf on Y and you have a line bundle on Y, you can twist. You can just tensor product. Take the tensor product. All right, that's operation number one. So gerbs are good for twisting. And another operation is another kind of twist, which we're going to use extensively. So suppose you have a group and you have something in the center. Let me call it gamma. And this will be called G prime. And so gamma is in the center of G. So to this operation, to this datum, you can attach the following construction. So if you have a gamma gerb over Y, you can twist G and obtain a twisted form of G over Y. Can form G, let me call it gerb, script G. It's a group scheme over Y. It's a general construction, just I'll leave it to your imagination how to do it. So gerbs are locally trivial, so like locally on Y nothing happens, but some interesting happens on the overlaps. And like, so I'll let you play with it. Just unwind the definition of gerbs to see this construction. All right. So that was all the recap. Now new stuff will begin. I'm wondering, what should we do? Shall we make like a 3-minute breathing pause just for people to catch their breath? And maybe people who want to flee, they can flee? Because I don't want to torture people. So let's have like 3-minute pause. And I'll look away and the people can. All right, let me resume. So now we launch into the discussion of two Fourier Mukai transform. So here's the formalism. So for the usual Fourier Mukai transform, we started with a pair of abelian group prestacks which paired to GM. This is for usual Fourier Mukai, aka Fourier. Zero Fourier Mukai. So this is the one Fourier Mukai transform, which is just the usual Fourier Mukai transform. You start with a pair of abelian group prestacks, but the pair to BGM. In other words, the datum of departure is a line bundle on the product. And for the 2 Fourier Mukai transform, you start yes, and what this was good for, you could use this line bundle to construct a functor from quasi-coherent sheaves on A1 prime to quasi-coherent sheaves on A2 prime. And the way you did it, you pulled back, tensored by this line bundle, I just erased it, and pushed forward. 2 Fourier Mukai transform, what do we want here? They pair to what? What's the target? i.e., you give yourself a GM gerb on the product. Who said B2 GM? Okay. Okay, if you said it, give me the formula for Fourier Mukai, 2 Fourier Mukai transform. So I start with C, which is a sheaf of categories on A1 double prime, and I want to create 2 Fourier Mukai C underlined, which is a sheaf of categories on A2 double prime. What's your formula? So you can't go back. You must give it. Sorry. It's a trap. If you say one thing, you have to say another. Go ahead. Yeah, you need to use the gerb, like it's. Yeah, so it's like P2 so this is the gerb that corresponds to this. So that's all there is. So nice looking formula, but you it's well-defined operation, but you have to make sure that it produces something sensible. So let's consider examples. Oh, wait a second. I need examples. I should have examples of A1 double prime, A2 double prime, the pair to B2GM. Who can give me some examples of that? Somebody? Just give me something that pairs to B2GM. Starting from something we know. Let's say something has to do with finite groups. Somebody help me. Don't be afraid. It won't influence your final grade. The question is, I want an example of this situation. You gave me the formula, but give me one situation in which I can apply it. None? All right.
Yes, we can take two classifying spaces of groups.
Great. Okay, that's my example 2. Give me my example 1. All right, what I mean is this. You had gamma and gamma check that paired to BGM. Just take B2 on one of them. So you can take B gamma, B2 gamma, so gamma times gamma check paired to GM, and you can de-loop twice the first argument. So, and that gives us, all right, so this will define the Fourier Mukai transforms from sheaves of cat on B2 gamma, 2 sheaves of cat on gamma check. And I want to show that in this example, this Fourier-Mukai transform works, that it really is an equivalence. So I won't decode the definition, I just, some plausibility check. I want to identify the two sides. Let's start with this side. So gamma check here appears as a discrete set. Sheaves of categories on that, it's just categories indexed by gamma check. So it's like, let me call it DG cat gamma check. It's really, for each element of gamma check, you have a category. Let's decode this. A long time ago, we said what sheaves of categories are on B of something, and this is B of gamma. So this is categories with an action of, you can say categories with an action of quasi-co B gamma. But we also had, and so B gamma is perceived here as a group, and this quasi-co is considered as a monoidal category under convolution. Let's remember, we also had the usual Fourier-Mukai transform, which said that this category is the same as quasi-coherent sheaves on gamma check with respect to the pointwise tensor product. And so what is this category? It's like you have a vector space sitting at every point of gamma check. You have a bunch of idempotents. So here you have a category on which you have all these idempotents indexed by gamma check. So this is really on the nose, DG cat gamma check. So two Fourier-Mukai in this case gives this tautological equivalence. So that's what it looks like in this example. And so now let me go to example 2. So I also start with gamma and gamma check, but I'll take B gamma times B gamma check, and that will go to B2GM. And let's see what things look like in this case. Actually, it's a good exercise. I leave it to you. So the two Fourier-Mukai transform will also give an equivalence between sheaves of categories on B gamma with sheaves of categories B gamma check. All right, so this is all I wanted to say about two Fourier-Mukai transform. But now we'll see examples. So here's kind of the main thing. So I'll tell you who my A1 and A2 are in real life. I start with a abelian group, finite abelian group gamma, but I'll take A1 to be the space of gerbs with respect to gamma on my curve X. And I'll take A2 to be the space of gerbs with respect to gamma check, but with a Tate twist. So like if gamma was mu n, nth roots of unity, gamma check is z mod n z, and mu n and of 1 will be again mu n on the same curve. And so the amazing thing is that we have a canonical pairing to B2GM. Question to the audience, is this something familiar? So finite abelian group, take gerbs on the curve, and then you take the dual finite abelian group, also gerbs on the curve. I claim you can pair them to GM. Is that something that you've ever seen? So this is what Verdier duality is on Verdier duality with for étale cohomology with coefficients at finite abelian groups. It says exactly that. So this pairing is called Grothendieck-Verdier duality. So let's just make it more explicit. So like if you choose a point on the curve, you can, so yeah, maybe I should have said before. So when I write gerbs with respect to some A on gamma, all I mean is again the same old mapping space, mapping stack from, sorry, on Y, from Y to B to A. So if you think of what this pre-stack of gerbs is on the curve, like non-canonically splits at the product. So like G gamma on the curve is a product of the finite abelian group, which is H2 times BH1 times B2H0. And if you do it for this twisted dual, let's see what we have. We have, well, H2 H0 So, and I claim that all of these guys will pair crisscross. See, so this group here, this finite abelian group here, by classical verticality as we know it, is just dual to this. So therefore they're dual, therefore if I apply B2 to one, it'll pair to B2GM. Now, these two finite abelian groups are dual to each other by Verdier duality. And again, when I apply B to both, it'll map to B2GM. And also, this abelian group is dual to this. And note the appearance of the Tate twist. So like if you take H2 on the curve with finite coefficients, it will be your group of finite coefficients of negative Tate twists. That's why kind of this one appears. So it all matches perfectly, and you obtain this pairing. And basically, from the analysis I gave here, like with this, my examples 1 and 2, it follows that the 2 Fourier Mukai transform, in this case, is an equivalence of categories. So, kind of lemma, 2 Fourier Mukai is an equivalence between sheaves of categories on gerbs with respect to gamma on the curve, two sheaves of categories with respect to on gerbs with respect to the dual on the same curve. All right, so that was the theoretical part of my talk. So what I wanted to conclude with is the applications of this to Langlands, kind of. So here what I'm saying is that to every sheaf of categories over this space of gerb, there corresponds to a particular sheaf of categories of this space of gerbs. What I was going to say now is that under this bijection, some very particular sheaf of categories here goes over to some very particular sheaf of categories over there. And both these sheaf of categories have to do with different sides of Langlands. And this statement that under this bijection something goes to something has implications. So it has Langlands content. However, this really may go beyond what the audience expects, and according to the schedule, I'm supposed to end now. So what we can do, we can announce formally the end and declare the rest kind of Q&A, and then I'll say my last few words. Does that sound okay? Yeah. Cool. So people can flee if they don't want to hear the L word. All right, so here's the Langlands content. So I'll construct a guy here and a guy here, and I'll say that they correspond to each other under this bijection. So here are the two guys. So what does it mean to construct a sheaf of categories of the space of gerbs? Like, it basically means I give you a gerb, and you give me a gerb, I have to give you a category. So that's what I'm going to do. So let G be a gerb. With respect to gamma, with respect to, so who is gamma and who is gamma is the center of my group G, and gamma check of 1 is pi 1 of G check. So I explained that the actual dual of gamma is the pi 1 algebraic, and if you twist it by 1, you get the actual pi 1 of the G check. So I give myself a gerb with respect to the center of G, and I'll construct a category. So here's what this category is. Remember, I have this short exact sequence, G adjoint, and so during my recap, I said there was the following procedure. Having a gerb for this, I can twist G. So I can form this twisted group scheme G, and then I can consider the same players. I can consider Ban, but already with this twisted group, and I consider the category D modules on it. And the totality of such for every gerb, I'll denote by D mod Ban G underlined with the superscript ZG. So this is the sheaf of categories over the space of gerbs with respect to the center, such that for every particular gerb, I get this category. So this is the player on the geometric side of Langlands. So now I'll explain the player on the spectral side of Langlands. So in the title of my talk, I said that non-constant group schemes will appear, and that's exactly what happens. So this is a non-constant group scheme. So now for the other side of Langlands. So I want to construct a sheaf of categories. I'll denote quasi-co underlined on the space of local systems with respect to G check on the curve. It will be pi 1 of G check. So I want to construct this guy. So what does it mean? It means that for every particular gerb with respect to this, I want to construct a category. So here's how I do it. I consider another short exact sequence which looks like follows. It'll be pi 1 of G check. Here it will be G check, the simply connected cover of it, and here I have G check. In fact, this sequence is the dual of that sequence. And so, by the same principle, having, let me call it G prime, which is a gerb with respect to pi 1 of G check on X, I can attach to it a twist of the Langlands dual. So by the way, these kind of twists are all over number theory, but people rarely consider this twist. So this is something kind of new. And, twist of G-check simply connected. So it's by means of a gerb for this, I can twist that. Check. And I can consider the category of quasi-coherent sheaves on local systems on this with respect to this group scheme. And so the theorem is that under this 2 Fourier Mukai transform, one guy goes to the other. So this is a theorem, and so let me draw two concrete consequences. So like you can really say what this theorem says in very concrete terms. So it says two things. One is the following. So start with the gerb for the center over the curve. And on the one hand, we create the category that is written here. On the one hand. On the other hand, you can do the following. So remember, we said that the space of gerbs with respect to ZG pairs with, again, space of gerbs with respect to pi 1 of G check to B2GM. So to this point, I can attach something that I'll call G tilde, which is a GM gerb on the space. So it's a GM gerb on the space of gerbs. So now the space, so this short exact sequence that I wrote here says that I have a map from the space of local system with respect to G check to the space of gerbs with respect to pi 1 of G check on the curve. So therefore, if I have this gerb on the target, I can pull it back. And the other category that I'll consider is this quasi-coherent sheaves in the original sense, but tensored by a gerb. So remember, I introduced this notion that I can take the category of quasi-coherent sheaves or an arbitrary sheaf of categories and tensor it by a GM gerb. So and that's what I'm doing here. So a particular one corollary is that these guys are isomorphic, equivalent as categories. And this is a statement with Langlands content. It says that the automorphic category for this non-constant group schemes, what is it in terms of the Galois side? And you can start guessing, like, do you have to modify local systems? And so for that reason, number theorists really didn't know the answer to this, but the answer is that you really have to modify the notion of quasi-coherent sheaf. You have to tensor by a gerb. And you can also do it not just for D modules, you can do it over algebraic closure of a finite field. You can take the trace of the Frobenius, and you will obtain a consequence for the automorphic functions. So that's consequence number one. Consequence number two, it's kind of you swap the roles, so, which is kind of symmetric thing where twisted group scheme is on the other side, and you twist by gerb here. And it also has kind of arithmetic consequences.